Okay, so what are we going to start today in coordinate complexes today? That is bonding in coordinate complexes. There are various theories which have been given for the bonding, nature of bonding between the central metal atom and the ligands. क्योंकि हमने क्या किया था? हमने किया था कि coordinate entity में जो central metal होता है, उसके साथ ligands अपने आप को coordinate करते हैं by donating a lone pair of electrons or sharing a lone pair of electrons to form special kind of bonds. Now the theories which have been proposed for bonding in coordination compounds, the first one that is known as valence bond theory. It is more commonly known as VBT. ठीक है? Second जो theory है, that is the crystal field theory. And the third theory which we have, that is the ligand field theory. Ligand field theory or molecular orbital theory, which is known as MOT. So we are going to discuss two theories over here. Molecular orbital, you've already done in class 11. So we are going to discuss two theories over here. One is valence bond theory, and the second one that is going to be crystal bond theory. So let's go on to the valence bond theory. The valence bond theory that was developed by by Pauling. Pauling was a scientist जिसने valence bond theory को formulate किया था और उसको develop किया था. Now over here, this theory is going to describe bonding on the basis of hybridization. Okay, so it is going to describe the bonding on the basis of hybridization of the central metal atom. Because the central metal atom that is going to have S, P and D, all three electrons, how do and which electrons are going to participate in bonding, that will depend on how the bonding is going to take place. और जो p orbitals participate करेंगे bonding में, they first have to come to the same energy level. So for that hybridization that is going to take place. So what kind of hybridizations we are going to study over here? We will study sp3, we will study dsp2, and we will study sp3d2. ठीक है? So these are the three hybridizations which are going to be most common with respect to the coordinate compounds. Now this theory is mainly going to deal with geometry and magnetic properties of coordinate compounds. Magnetic properties matlab they may be paramagnetic, they may be diamagnetic depending upon the paired and unpaired electrons present. If all the electrons they are going to be paired, the coordinate compounds they are going to be diamagnetic. And if even one single electron that is going to be unpaired, the compound is going to be paramagnetic. And it is seen that as the number of unpaired electrons will increase, the paramagnetism that is also going to increase. So this all we are going to study according to this theory. Now let's go on to the postulate of this theory. When we are looking at the postulates of this theory, the first postulate says that the central metal atom loses electrons. Central metal atom loses electrons to form ions. Right? So the central metal electron that is going to lose electrons to form ions, and those electrons they are going to be equal to the valency of that particular central metal atom. For example, if we are taking iron, so iron can exist in two oxidation states, Fe2 positive and Fe3 positive, right? So Fe2 positive is losing 2 electrons, which is again the valency of iron. Fe3 positive is going to lose 3 electrons, so that is again the valency of iron. Similarly, we are talking of chromium. Chromium has a tendency to lose 3 electrons and enter into Cr3 positive state. Then we have cobalt. Cobalt can enter into CO3 positive state. We have nickel. Nickel can enter into Ni2 positive state. ठीक है? So जो उसकी valency होती है, उसके accordingly it is going to lose electrons. So this is the first postulate. Now over here, the second postulate is that the central metal atom makes available a number of vacant or empty orbitals for bonding. Okay, now ये जो empty orbitals वो bonding के लिए, because what is going to happen, the ligand is going to donate the electrons. So when it is going to donate the electrons, those electrons need some space to sit at, and that space is provided by central metal atom in the form of empty orbitals. Those empty orbitals may be those of Ns, they may be those of Np, they may be those of Nd, and they may also be those of N-1d. Okay, so all of these empty orbitals, they are going to be present. Now these vacant orbitals over here, they are going to hybridize. So hybridization of vacant d orbitals take place, so that all the orbitals which are participating in bonding, they are same in number and they have comparable energies, because always bonding of those orbitals can take place which have same energies. ठीक है? So जितने भी ये vacant d orbitals या d भी ना लिखो, अगर आप ns np भी participate कर रहा है, तो जितने भी vacant orbitals participate कर रहे हैं bonding में, उन सब की hybridization होनी जरूरी है. So let's see what is the kind of hybridization and geometry which we get. Okay, so when we talking of coordination number of 2, the type of hybridization that is going to take place is sp. ठीक है? The geometry over here, that is going to be linear. And example which we can take over here, that is of AgNH3 whole twice positive. So this is going to be the example. Okay, now let's take, if the coordination number that is going to be 3, the hybridization is going to be sp2, the geometry is going to be trigonal planar. An example which we can take over here is that of Hg I3 negative. Okay, then number 4. If the hybridization is sp3, the geometry is going to be tetrahedral, right? And the example which we can take over here is that of nickel carbonyl. There is going to be no charge, 0 होता है. Nickel carbonyl, ठीक है? Also, if the coordination number over here is 4, we have another kind of hybridization which is going to be dsp2, and the geometry over here, that is going to be square planar. ठीक है? और square planar का example हम ले सकते हैं nickel CN4 2 negative. This is an example which we can take over here. The next type of hybridization which we have, that is dsp3. 5 coordination number, dsp3 or sp3d, either of the two. Now in both the cases, if the geometry is dsp3, if the hybridization is dsp3, the geometry is going to be ट्राइगोनल पिरामिडल, ठीक है। सो यहाँ पे हमारे पास जो एग्जाम्पल एक हम ले सकते हैं, दैट इज दैट ऑफ FeCO5, राइट। तो यहाँ पे द सेकेंड टाइप ऑफ हाइब्रिडाइजेशन इज sp3d. So sp3d में geometry becomes square pyramidal. What is the difference between both of these? dsp3 means that n-1d that is going to participate. Okay, that is the inner d orbital. sp3d means n d orbital is going to participate, which is the outer orbital. Okay, so this we will do in detail when we are going to do the examples of valence bond theory. So in case of dsp3, the geometry is trigonal pyramidal, and in case of sp3d, it is going to be square pyramidal. Example which we can take over here is that of SbF5 2 negative. ठीक है। Similarly, if the coordination number that is 6, if the coordination number is 6, there is going to be two types of geometries. The first one, that is D2sp3. This is known as, the geometry is going to be octahedral, and this is known as inner orbital complex, which means that the inner d that is going to participate in bonding. Example which we can take over here is that of FeCN6 3 negative. FeCN6 3 negative. The other type of hybridization is sp3d2. Again, this is also going to be octahedral, but over here outer d is participating, so this is known as outer d complex. ठीक है। An example which we can take over here is that of FeF6 3 negative. We will do all of these later. FeF6 3 negative, right? So over here, this is according to our second postulate of valence bond theory, that the hybridization that will depend upon the s, p and d orbitals which are going to participate in bonding. Then we come to the third postulate of VBT. The third postulate says that the non-bonding electrons of the metal occupy the inner orbitals, right? So the ones which are not going to participate in bonding, they are known as non-bonding electrons occupy the inner orbitals. Okay, non-bonding electrons, they are going to occupy the inner orbitals. So d orbitals which are participating in this can be either the inner orbitals, as we have done over here. When we are writing it is d2sp3, it means n-1d is participating. That means अगर हम यहाँ पे 4s भर रहे हैं, यहाँ पे 4p भर रहे हैं, तो ये 3d है. So 3d, 4s, 4p. When we are writing this d outside, outwards, so it means nd orbital is participating, which means that this is 4s, this is 4p, then this is 4d, which is going to participate in bonding. Okay, so this is how we say that the complexes may be inner orbital when n-1d is going to participate, or it may be outer orbital when nd that is going to participate in bonding. Is it clear? फिर उसी के basis पे जब जो भी inner orbital होते हैं, they are referred to as low spin. We will do this later. So the inner orbital complexes, they are going to be low spin, and the outer orbital complexes, they are going to be high spin. We will just discuss this later. What does this mean, right? Then we come to the ligands. They have at least one sigma orbital. We've spoken of all the characteristics of the metal over here. Now we are going to talk about the ligands. So the ligands, they have at least one sigma orbitals containing a lone pair of electrons. So all the ligands, they should have lone pair of electrons, right, to donate to the central metal atom. Okay, so यहाँ पे they are going to form a kind of bond which is known as, represented as, first of all, ligand to metal, and this arrow, this is representing a coordinate bond, which means that the ligand that is donating its electrons for sharing, there is going to be no ion formation because ligands, they are not parting away with their electrons, they are only sharing their electrons with the central metal atom. Is it clear? So this is how a coordinate bond that is going to be this thing formed. Then number 5, it is possible to predict the magnetic properties depending upon the paired and unpaired electrons. So we already know that if the electrons are paired, so with regards to the magnetic properties over here, if all the electrons are paired, the substances or compounds, they are said to be magnetic. Okay? And if there are unpaired electrons present, the compound is said to be paramagnetic. Now what are diamagnetic compounds? Which are going to be repelled by the magnetic field, and paramagnetic compounds which are going to be attracted by the magnetic field. Okay? So these are the postulates. Based upon these postulates, we are going to discuss the structure, the magnetic character, and the hybridization which is involved in some of the compounds, and how do we formulate any compound which is given to us. Okay? Okay, so let's go on to certain examples. The first example which we are going to do is of coordination number 6. Examples to exhibit VBT. Now over here, when we are talking of complexes of coordination number 4, we've already seen that the complexes of coordination number 4 may either undergo sp3 hybridization or it may undergo dsp2 hybridization. Okay? So over here, they may be either tetrahedral or they may be either square planar. So in case of tetrahedral, the geometry is going to be sp3, and in case of square planar, the geometry that is going to be dsp2. Okay. Now when we are talking of hybridization over here, the geometry we have already discussed. This geometry now will depend, or the hybridization will also depend upon two things. Number 1, the approaching ligand. What kind of ligand that is going to approach, right? And number 2, it will also depend upon the kind of metal which we are taking. So as we have done that, there are certain elements, we will also do some exceptions when we are doing the examples over here, but otherwise there are certain compounds of platinum which should be tetrahedral but they adopt square planar geometry. That is because of the larger size of the d orbitals of platinum. Okay? Otherwise उसकी होनी चाहिए थी sp3 पर वो dsp करते हैं because the cloud of the d is going to be diffused. तो उसकी वजह से instead of another p which is going to participate, it is the d which will participate in the hybridization. Okay, so let's see how we are going to form. The first example which we are going to do is that of nickel Cl4 2 negative. The first thing over here is to calculate the oxidation state of the central metal atom. So oxidation state of central metal atom, that is going to be +2. Okay, then we write down the electronic configuration of nickel. Electronic configuration of nickel हमारे पास क्या आ गई? Argon 3D84S2. Okay. Then what is the electronic configuration of Ni2 positive? The electronic configuration of Ni2 positive, the electrons will be given out from 4s. So we have argon 3D8. Now we will draw the orbital picture. We have nickel. Nickel has 3D. Okay. Then 4s. And then 4p. So this is 3d, 5 orbitals, 4s and 4p. So there are 8 electrons. We have 1, 2, 3, 4, 5, all singly filled, 6, 7 and 8. Okay? And there are going to be 2 electrons in S. P over here, that is empty, as you can see. Now when we are going to Ni2 positive. In case of Ni2 positive, 2 electrons, they are going to be extracted or removed from 4s. So this is now going to be rendered empty. And in case of 3d, what do we have? 8 electrons intact. Okay. Now there are 4 ligands over here. For those 4 ligands, there should be how many? There should be 4 empty orbitals present. Right? Now it is seen that chlorine, which is the ligand over here, that is a weak field ligand. We will discuss of weak field and strong field ligands when we go on to CFT. Because when valence bond theory was given, the clarity of weak field or strong field was not there. So I am only telling you about weak field and strong field so that we come to know that how the hybridization that has to be formed. Now chlorine over here is weak field. The weak field ligands, they do not have the tendency to force pairing. Okay, no rearrangement of electrons will take place if there is weak field ligand present. So chlorine, all the halides, they are going to be weak field. Okay, all halides are weak field. The strong field ligands, they have a tendency to rearrange the electrons in D. Now as chlorine is weak field over here, there is going to be no rearrangement of electrons. If there is no rearrangement of electrons, we have 1s and 3p which is going to be empty. So the chlorine that will donate electrons in these empty orbitals and the hybridization is going to be sp3. Okay? So let's see what is happening over here. When we are going to the complex, how are you going to show the complex over here? 5, 3, ठीक है? यहाँ पे ये सारे वाले ऑलरेडी फिल्ड है. Okay. Now over here, chlorine is all the chlorine. They are going to give its electrons. Each chlorine has one lone pair of electrons which it is going to donate. And the overlapping of the electrons may be shown by dotted lines. Right? So, by looking at this valence bond theory ka structure, what are going to be the characteristics of this particular compound? Number 1, the hybridization is sp3. Therefore, the geometry is going to be tetrahedral. Okay? Now you can see over here that there are 2 unpaired electrons present. If there are 2 unpaired electrons present, it means that the complex is going to be paramagnetic in nature. Is it clear? So this is how you come to know about the paired, unpaired and geometry over here, depending upon the kind of ligand. Okay? So again I am saying all the weak field ligands, for example halides is a weak field ligand, water is going to be a weak field ligand. All these weak field ligands do not rearrange the electrons in the d orbital. Now we are going to take an example of a strong field ligand so that you can compare both these structures. Okay, so we're taking an example of nickel, CO4. Now in this case, the oxidation state of nickel, that is going to be 0. So if the oxidation state of nickel is 0, that means nickel will not go into the ionic state. Now the carbonyl over here is a strong field ligand. Because it is a strong field ligand, it is going to help in the rearrangement of the electrons in the inner d orbitals. Okay? So let's go on to, again you can write the electronic configuration on this side. I'm directly going on to the orbital picture over here. So nickel has 5, 4s and 4p. Okay, so in 3D we have 1, 2, 3, 4, 5, 6, 7 and 8. And in 4s we have 2. Okay, now as carbonyl is a strong ligand, there is going to be rearrangement which is taking place over here. So electrons from S, they jump to the orbitals having single electrons, such that the rearrangement can now be shown as so we have over here all paired electrons. There are all paired electrons which are going to be present such that S and P3 they are rendered empty. ठीक है? So अब जब ये empty हो जाएंगे तो complex that can be shown as show the complex over here. Now from this orbital picture, what can you see? You can see that all the electrons over here, they are going to be paired. So if all the electrons they are paired, first of all, what is going to be the hybridization? Hybridization is sp3. The shape or geometry is going to be tetrahedral. Okay? And we have over here, because all are paired, therefore the complex that is going to be diamagnetic. Is it clear? Right? So this is how you want to show tetrahedral. Now let's take an example of square planar complex. So when we're doing a square planar complex, we are going to take an example of nickel CN4 2 negative. Again the oxidation state is going to be 2 positive and Cn that is going to be what? That is going to be a strong field ligand. So again there is going to be rearrangement over here. Let's write down. First of all, nickel ka we have so then we draw it for nickel 2 positive. I'll fill in the electrons together. Right, so 3d8 in nickel we have to fill 1, 2, 3, 4, 5, 6, 7 and 8. Okay, and we have 2 over here. In case of Ni2 positive, 2 electrons from S they are going to be removed. So we have 1, 2, 3, 4, 5, 6, 7 and 8. Now as I just said that cyno is going to be a strong field ligand. So over here the rearrangement of electron is going to take place. Okay, such that when we are drawing the complex over here, this orbital will be now empty because the electron from this D has gone over here. So we have over here 1, 2, 3, 4, 5, 6, 7 and 8. ठीक है, और यहाँ पे हमारे पास क्या है? Sino are 4, so 1 goes to D, second, third and fourth. So this is how we are going to show. Now what can you see over here? You can see that the D orbital is participating in bonding. So the hybridization and inner D is participating. So hybridization is going to be dsp2. Okay? The geometry is going to be square planar. And as all the electrons are paired over here, therefore this is going to be diamagnetic in nature. This is going to be diamagnetic in nature. Is it clear? Okay. So next what we are going to do over here, we are going to take another complex which has platinum, then cyano. So this is for your homework. You have to draw these. You have platinum, CN4, 2 negative complex. Platinum, CN4, 2 negative complex. And the other one which we have is CO, NH3, 4, 2 positive complex. Okay, so you try and draw the structures for these two. If we find any difficulty, we will discuss this tomorrow. Okay, then we go on to complexes with coordination number 6. Complexes with coordination number 6. तो उसी तरह से आपने इसको भी draw करना है. There are going to be 6 different ligands, right? So in this, when we talking of complexes with coordination number 6, there are going to be 2 types of complexes. One which are known as inner D complex. In case of inner D complex, as I have already told you, n-1D that is going to participate in bonding, right? The hybridization is going to be D2sp3. D2sp3, and they are also known as low spin complexes. They are also known as low spin complexes. Okay? The second one which we have, they are outer orbital complex. In case of outer orbital complex, ND that is going to participate, and the hybridization is going to be known as sp3d2, and these generally form high spin. Now the difference between low spin and high spin, generally what we take is that in case of low spin, the number of unpaired electrons, they are going to be less, and because the inner d orbitals are going to participate, the spin of these are going to be less. Okay? And in case of outer, the number of unpaired electrons may be more, and because the outer orbitals, they are participating, as a result of that, they are going to have high spin complexes. Right? So we are going to discuss both of them over here. The first one which we will discuss is inner orbital complex. In case of inner orbital complex, we may have again weak field ligands and strong field ligands. We are taking an example of amine complex. ammonia over here is going to behave as a weak field ligand. Okay? So let's go on to inner orbital complexes. When we're doing the inner orbital complexes, over here we have CuNH3 6, positive. Okay, this is the complex which we are going to do. Copper ही लिया है हमको. What is going to be the electronic configuration? Copper नहीं, chromium है. What is going to be the electronic configuration? We have argon 3d5 4s1. The oxidation state is going to be 3 positive. So 3 positive की outermost electronic configuration क्या हो जाएगी? Argon 1 electron from here and 2 from here. 3d 3. Okay, so we go on to the orbital picture. I am directly drawing that for Cr3 positive, but you also have to show for chromium separately, right? So Cr3 positive means this is what we have. We have 3 electrons. Okay, there are 6 ligands. So we need 6 ligands which should be empty after the filled ones. So we have 1, 2, 3, 4, 5, 6. There is, as it is, it's a weak field ligand. There is going to be no rearrangement of electrons taking place, right? So complex हम कैसे draw करेंगे? So we have 3 electrons over here, and there are going to be 6 pair of electrons. 1, 2, 3, 4, 5 and 6, which are going to be provided by the ligands. So we have NH3, NH3, and NH2. Okay, and you can show the overlapping by dotted lines like this, right? So over here you can see that the hybridization in this case, that is going to be B2sp3, and the shape or geometry is octahedral, right? And it is inner D complex. So it is going to be low spin complex over here. We've already done that. Inner D, they are going to be low spin complexes, and it is going to be paramagnetic. So this is exactly how when you are writing your boards ka paper, this is exactly how you're supposed to give the answer of any. Okay, and in case of your competitions, the questions which you will get ki whether this complex or which of the following complexes are inner orbital complexes, या which of the following complexes they are going to be paramagnetic complexes. So this is the type of questions which you are going to get. Okay. Now we will discuss another example of outer orbital complex. So outer orbital complex, what are we going to get? We are taking over here. Okay, let's take the example of COF6 3 negative. Again, F over here is going to be weak field ligand. Okay, what is going to be the oxidation state of cobalt over here? +3. What is the electronic configuration of cobalt? Argon 3d7 4s2. What is the electronic configuration of CO3 positive? It is going to be argon 3d7, 2 ये निकले और 1 ये निकला. So it is going to be 3d6. So let's quickly just form. Directly I am again putting 3 positive, but you have to give the orbital picture of both. Okay, so 6 means over here 1, 2, 3, 4, 5 and 6. Now what can you see over here? You can see that fluorine is going to be a weak field ligand. So in this case, it is going to be the outer d orbitals which will participate in hybridization. Okay? So this is 3d, this is 4s, this is 4p, this is going to be 4d. Because fluorine is a weak field ligand, there is no rearrangement of the electrons which is going to take place. So the outer D will participate in bonding, right? So I am showing it here only rather than drawing it again. We have 1, 2, 3, 4, 5, 6 empty orbitals which we need. Six, and the overlapping, but you have to draw it separately, please remember. Overlapping is going to be shown like this, and we have fluorine, fluorine, okay. So now when we are writing the characteristics of this, how will we write? Number 1, hybridization is going to be sp3d2. Okay. Number 2, it is outer orbital complex. Number 3, it is high spin. You can see that the number of unpaired electrons in this case, that is going to be 4. And finally, it is going to be paramagnetic. Right? So this is what you need to do. You can take another example and help yourself doing it. We have H2O6 3 positive. Again, H2O is going to be taken as a weak field ligand. So this is going to form outer D complex. Okay? So this is what our valence bond theory is, and this is how we come to know. But now this theory has a lot of limitations as well. Right? Although it gives us some, in fact, complete idea about the magnetic character, but still the theory does not explain the spectra of complexes. Spectra means why they are going to be colored. All the coordinate complexes are going to be colored because most of them, of course, because of the fact that they have empty d orbitals or they have unpaired number of electrons. Okay? So, valence bond theory does not tell us why the spectra of these compounds they are going to be colored. Right? Now, also it does not give us an idea of the strong field and weak field ligands. Which means it does not give us an idea why the rearrangement of the electrons that is taking place in certain complexes. So, we've already seen that with strong field ligands there is going to be rearrangement. Right? Why that rearrangement takes place, that is not explained by VBT. That is more clearly explained by CFT, which we will do in our next lecture. Then it does not tell us the existence of the inner D and the outer D complexes. Okay? It will not tell us the complex, so we're just saying because of the fact that we are drawing the pictures over here, it does not give us an explanation to this. Okay? Then the theory does not explain why certain complexes are reactive, whereas certain complexes they are going to be inert. So all these drawbacks they were further explained in a modified theory which was known as the crystal field theory, which we will do in our next lesson. Okay?